All right, y'all. Today we are going to talk about accumulations and approximating areas under a curve with Riemann sums. So we're going to start out by talking about how many scones are in supply. So we got a bakery. They make scones at a rate of 40 scones per hour. So that's a rate. That's a derivative. Remember, rate is slope is derivative. The bakery staff begins making scones at 4 a.m. and opens to the customers at 7 a.m. and they stop making scones at 2 p.m. So, how many scones has the bakery made by the time the bakery opens? So, we know that the rate is 40 scones per hour. And we know the amount of time that they were baking scones is 3 hours. So for my stoichiometry people in chemistry, you'll realize that this is hours over 1, and your hours will cancel out and leave you with 120 scones. So what I want you to take away from this is what you've done is rate times time gives you quantity. All right, so during the morning rush from 7 a.m. to 10 a.m., customers buy scones at a rate of 60 scones per hour. So notice that this is another rate. So between 7 and 10 a.m., is the bakery's supply of scones increasing or decreasing? Well, we know that the supply is decreasing because the scones are being removed. In other words, they're being purchased faster than they're being made. So from 10 a.m. to 3 p.m., the rush is over and the sales drop to 25 scones per hour. We know the bakery closes at 3 p.m. So at what rate is the bakery's supply of scones changing? So reminder, they stop making scones at 2 p.m. So for the last hour, they're not making scones anymore. So between 7 and 10 a.m., let's talk about the rate. The rate is going to be 40 scones per hour, but then they're being removed at a rate of 60 scones per hour. So the rate is negative 20 scones per hour. I'm going to call that S per H because I'm being a little lazy. Then between 10 a.m. and 2 p.m., they're still making scones. So they're still being added at 40 scones per hour. But this time they're only being purchased at a rate of 25 scones per hour. So now positive 15 scones per hour. And then finally, between 2 and 3 p.m., no more scones are being made and they're still being purchased at a rate of 25. So the rate is negative 25 scones per hour. So what we're going to do is write a piecewise equation for the rate of change. Remember, these are the 3 rates of change that we're going to make. And so really we're going to do 4 because we're going to talk about before the bakery opens as well. So from 0 to 3, from 4 a.m. to 7 a.m., what is the rate of supply? The rate of supply is going to be 40 because they're making scones, 40 scones an hour, and they're not being removed. Then from 3 to 6 hours, that's 7 a.m. to 10 a.m., they're being removed from negative 20. And then from 6 to 10 hours, or from 10 a.m. to 2 p.m., they're at 15 because they're making more than they're selling. And then finally, between 2 and 3, they're not making them, they're only selling them. So negative 25. So we're going to make a piecewise function that represents the rate of change of these scones, S of t. So now we're going to graph it. So between 0 and 3, we're going to have a height of 40. Between 3 and 6, we're going to have a height of negative 20. Between 6 and 10, we're going to have a height of positive 15. And then finally, for the last hour, we're going to have a height of negative 25. And don't worry too much about the open or closed circles on the ends of these. But we're using open circles except for right here because that's what the intervals have given us. We could use closed circles with the equals, so otherwise we use open circles. So when is the overall supply of scones in the bakery increasing. How do you know? Well, we know between 0 and 3, the number of scones is increasing because the rate, remember this is the rate is positive. So how do we know? We know it's between 0 and 3, and also between 6 and 10. Because S of t is greater than 0. So in other words, the rate is positive. And if the rate is positive, that means that the amount is increasing. So when is the amount of scones in a bakery decreasing? Same deal. Decreasing happens when rate is negative, and that occurs between 3 and 6, and then from 10 to 11. So when t is between 3 and 6 and 10 and 11, because S of t is negative, and that means that the rate is negative. A negative rate, a negative derivative, means your original function is decreasing. So how many scones are in stock in the bakery at 10 a.m.? We want to know at 10 a.m. So when does that occur? What hour? That occurs at the 6th hour because they open at 4 a.m. So we want to know how many scones are in the bakery when we've hit this point. So what do? We know that for the first 3 hours, we are making scones at a rate of 40 scones an hour for 3 hours. So 40 scones an hour for 3 hours. Plus, and then we know from up here that between 7 a.m. and 10 a.m., the rate is negative 20. So for the next 3 hours, scones are being removed faster than they're being added. So negative 20 for the next 3 hours. And when we add that together, we end up with 60. So there's 60 scones at 10 a.m. because for 3 hours they were being added at a rate of 40, and then for another 3 hours they were being removed at a rate of 20. So find the area between each section of the graph and the t-axis. So the x-axis here is the t-axis because as time is going along, that's t. So let's find the area between each section of the graph and the t-axis. So area below the t-axis is negative. And that's kind of weird because normally when we talk about area, we're talking about physical space. And it's weird to think about physical space being positive or negative. But here, we're not talking about physical space. We're talking about a derivative here. We're talking about a rate being positive or negative. So let's actually find the area. So the area of this has a width of 3 and a height of 40. So the area of this is 120. Here, this has a width of 3 and a height of negative 20. So the area is negative 60. And again, I know that feels kind of weird to have negative area, but it's okay. And from 6 to 10, that's a width of 4 and a height of 15. So that's 60. And then from here, we've got a width of 1 and a height of negative 25. So this is negative 25. So what does the area under S of t represent? It represents scones being accumulated. So in these spots, 120 scones are being added. Here, 60 scones are added. Here, 60 scones are removed. So the word we use is accumulation. And sometimes accumulation is positive. That means scones are being added to the inventory. And sometimes accumulation is negative. That means scones are being purchased and removed from the inventory. So accumulation of scones. So how many scones are left in the bakery when it closes at 3 p.m.? Well, we start with 120 scones after the first 3 hours. Then they're being removed for 3 hours, so we lose 60. Then we make more scones. At the end of that period, we've gained 60 and then minus 25. So at the end of the day, there are 95 scones left in the inventory. So what we've done is we started with a rate and we found the area underneath these lines. So the area under rate of change gives us an accumulated quantity. Another way to think about this is just kind of a preview is the area under a derivative gives an output. Interesting. So here are the units for area. Whatever the rate of change is, we abbreviate this as ROC a lot of times. So the rate of change times the independent variable, and a lot of times this is time. So this is just rate times time. So for example, we might have a rate of gallons per minute times a minute, and that will give us gallons. So what that is it's referencing earlier here, we had scones per hour times hours, and that just gave us the leftover scones. That's what happens here. That's how we get accumulation. So the area above the x-axis is positive area, and it represents the quantity increasing. And then the area below the x-axis is negative area, and it represents the quantity decreasing. All right, let's look at a couple examples. So for example 1, the velocity of an ant traveling on a straight path. So remember, velocity is a derivative of the position function. So if we want to know what's accumulated, we can move from derivative up a level using the area under the curve. So the velocity of an ant traveling on a straight path is modeled by the function v, where v of t is measured in inches per second. So here's inches per second, and then t is measured in seconds. So does the ant travel further between t equals 0 and 2 or between 2 and 4? How do you know? Well, let's figure it out. So between 0 and 2, we know that the accumulation can be modeled by the area underneath the curve. So here, if we want to find the area of this is a triangle. So base times height, 2 times 4, divided by 2. This is an area of 4. So between 0 and 2, the area is 4. Then between 2 and 4, that's a rectangle. Between 2 and 4, that's a width of 2 and a height of 4. So the area is 8. So, and the ant traveled faster, or sorry, farther. Further or farther? I don't know. Between t equals 2 and t equals 4 because area under is greater. And if we think about this realistically, it makes sense. Here we're talking about how the ant is speeding up. So the ant is starting off standing still and then gets faster and faster and faster during this interval. But here in the second interval, he's already at a speed of 4 inches per second. So he's not having to start from scratch. He's just cruising at this point. And if you're cruising at a faster speed, you're able to cover more distance. So it makes sense if we think about it logically as well. So describe the ant's motion between 9 and 12. So between 9 and 12, what is the ant doing? The ant is losing inches per second because it's a negative. So how do you lose inches per second? The ant is walking backward. So is the ant farther away from her starting point at 9 or at 12? It's farther away at t equals 9 because it walks backwards after that, which gets it closer to the starting point. So how many inches away is the ant from her starting point? at t equals 16. So what I want you to keep in mind while we're doing this is when we're finding the area under each of these curves, here we're doing width in seconds, and then we're doing height in inches per second. And when we do length times width, and we do seconds times inches per second, the seconds divide away and we're left with just inches. So when we're finding these rectangles, what we're really doing is we're just getting inches by itself, which tells us how far, how many inches. So the act of finding these rectangles or triangles is the act of finding how many inches. We're doing seconds times inches per second, and when we multiply these labels, we end up with just inches. So let's figure out how many inches this ant has traveled during the entire journey. So remember that negative means that they're walking backwards. So let's break this up into some pieces. So here's already 4. And then from here to here, this is 3 times 4. So this is 12. Here, this triangle has a width of 4 and a height of 4. So base times height divided by 2, this is 8. From here, we've got a width of 3 and a height of 1. So this is negative 1.5. And then here we've got a width of 4 and a height of 2. So this is 4. So if we add up all these numbers together, and remember this is negative because this is where the ant is losing inches. It's working backwards. If we add them all up, we will end up with 26.5 inches. And that's how many inches away the ant has gone from the starting point. All right, so now we've got Jada. Jada's riding her motorcycle, and here the velocity is given. So the velocity is given in kilometers per hour, and this is given in hours. So when we multiply these together, I want you to remember that kilometers per hour times hours is going to give us just kilometers. So that's why we're finding the area, is because when we multiply these units, we end up with just distance. So Jada's riding her motorcycle. Here's the velocity curve from 0 to 10. The graph of her velocity is shown. During what hour interval is Jada accumulating the most kilometers, and how do you know? Well, we want to know during what hour interval is the area the greatest, because that's when the kilometers are the biggest. And that happens between 9 and 10. So 9 to 10, because area under V of t is greatest. So not all areas can be found with simple geometric formulas. It's not going to be rectangles and triangles here. So we'll have to approximate. How do we approximate the area? We'll use 10 rectangles of equal width. So how will you determine the height of each rectangle? Well, you get to choose. So you get to choose the height you want to use for each rectangle. What we do know is that the width of all these rectangles are going to be 1 unit, because there has to be 10 in total. But there's different ways for you to choose the height. So ideally, if we were together, we'd be able to compare, but I'll show you some options. Some of you might choose starting at 0 and choosing 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, I lost it. 9, 10. And you might make those the height of your 10 rectangles. So they'd look like this. So that might be how you choose the height of your rectangles. And that's perfectly fine. But some of you might choose the height of your rectangles by starting at 1 and ending at 10. Instead of going from 0 to 9, you might go from 1 to 10. So yours might look like this. Start at 1 and go to 10. So your rectangles would look a little bit different. Yours might look like this. And here's the thing, y'all, there's no right answer here. There's just pros and cons. So depending on how you pick the height of your rectangles, you might get a different area. So your part D answer could be an overestimate, or it could be an underestimate. If you pick the left side points, so if you made points from 0 to 9, you're going to have an underestimate. But if you pick the right side points, so if you see I picked the right side points here, I picked all the points to the right, all of these rectangles make an overestimate. So whether you use rectangles that are too short or rectangles that are too tall, they'll give you an estimate of the area under the curve, but it might be over, it might be under. So what's a better way to get a better approximation of Jada's total distance rather? That would be more rectangles. We only use 10 rectangles, but if we use more rectangles, we're going to get a better approximation. So here is how we approximate areas with rectangles. And this is called Riemann sums because we find the rectangles and then we add them all up. That's the sum part. So to approximate the area under a curve on the interval a to b with n equals subdivisions, let b minus a over n be the width of each rectangle. So that means, for example, if you're going from 0 to 10 with 10 subdivisions, do 10 minus 0 over 10 to get a width of 1 for each rectangle. Then to find the height of each rectangle, you might do what's called an LRAM, which means we evaluate the function the left endpoint of each rectangle. We might do an RRAM, so right endpoint. Or we might even use the midpoints. And then the total area under the curve is going to be the sum of all the rectangles, and that approximates the accumulation. All right, so here we have an example where the rate at which a saline drip is administered to a patient is given by R of t here. So what we're going to do is we're going to use a right Riemann sum approximation with 4 equal subintervals. So what that means is we're just going to make 4 rectangles. Now we know how wide each rectangle is going to be, 15, 15, 15, and 15. So just to help you think about this visually, we're going to have a rectangle that's 15 units wide, a rectangle that's 15 units wide, and y'all, these are not to scale. These are not to scale. Okay, this is just to help us visualize. So we're going to have 4 rectangles that are 15 units wide. So how do we know how tall to make our rectangles? Because we're using a right Riemann sum, we're going to choose either the left side of the 15 or the right side of the 15. Well, the right side, because it's a right Riemann sum. So the height of this guy is going to be 2.7. Then we're going to do the same thing over here. The right side of this interval is going to be 4.2. We're going to use the right side of this interval, 3.8, and the right side of this interval, 1.9. So do we end up ignoring the 1.3? Yes, because we're only using the right side outputs. So then we're going to find the areas of these 4 rectangles. So you can write it as 15 times 2.7 plus 15 times 4.2 plus 15 times 3.8 plus 15 times 1.9. And when you put that in your calculator, you should end up with 189. So that tells us approximately how many liters, or milliliters rather, so milliliters, were administered from the first minute to, or the 0th minute to the 60th minute. So what does this represent? Well, we did milliliters per minute times minutes, and that gave us milliliters between the 0th minute and the 60th minute. So here's an important tip for the AP exam. On the AP exam, it's really important that you show a sum of products if you want full credit on these Riemann sum problems. So in other words, don't do any mental math. Don't do any mental calculations in the first step. Here's why. Example 3, the one we just did, this shows the length times the width of each rectangle. So this means something. Your exam grader would be able to see, oh, length times width, length times width, length times width, length times width, add them all up. Boom, boom, boom. If you write it like this, even though those are the correct products, they don't show your method of finding the areas of rectangles. So just skip this part entirely and just put this into your calculator. You'll be good to go. All right, last one. Consider the region enclosed between the x-axis and the function e to the x. Use a left Riemann sum approximation with 5 equal subintervals between -1 and 4. So to make our lives easier, let's make a chart. Our inputs are x values, and we're going from -1, 0, 1, 2, 3, and 4. And then our outputs are going to be e to the x. So that's going to be e to the -1, or 1 over e, 1 e squared, e cubed, e to the 4th. So we are going to do 5 equal subintervals. So we've got those intervals. They're each going to be 1 unit wide. So we're making 4 rectangles that all have a width of 1. But we're going to use a left Riemann sum. So when we choose the height of our rectangle, if we're making a rectangle here, how do we choose how tall to make it? We're going to use the left value. So we're going to have a rectangle with a width of 1 and a height of 1 over e. And we're just going to keep going. All of our rectangles have a width of 1. And then for this next rectangle, let me use a different color. We're going to use between 0 and 1, we're doing left, so its height is going to be 1. So 1, 1, plus 1 e, plus 1 e squared, plus 1 e cubed. So you might be saying, well, are we ignoring e to the 4th? And the answer is yeah, this is going to be an underestimate because we're choosing all the left side heights for each of our rectangles. So that's going to equal approximately, if you want to put this in your graphing calculator, this is going to equal approximately 31.561. So how do we use a midpoint Riemann sum? We're going to go halfway in between all of these, and we're going to have 5 subintervals. So if they're still going to have a width of 1, that's fine. But this time we're going to go in between. We're going to have e to the negative 0.5, because that's halfway between e to the -1 and e to the 0, plus 1 times e to the 0.5, plus 1 times e to the 1.5, plus 1 times e to the 2.5, plus 1 times e to the 3.5. So the midpoint Riemann sum means that we're going to substitute in x values that are halfway between all the x values we're given. So what we did is we substituted in x equals -1/2 here because it's halfway between -1 and 0. Here we substituted x equals 1/2 here because it's halfway between 0 and 1. Here we substituted x equals 1.5. I don't know why I switched to fractions because it's halfway between 1 and 2. Here we substituted x equals 2.5 because it's halfway between 2 and 3. And here we substituted x equals 3.5 because it's halfway between 3 and 4. And when you evaluate this, you should end up getting approximately 52.03